So after completing the derivation of the mass and momentum conservation laws, we would like to just stop a little bit before we jump into the energy equation and give some application or examples how to use both the momentum equation and the conservation of mass continuity equation into some application. So again, let's recap the final form that we got for both the continuity and the momentum equation. And I always like to write this equation in the more generic form. So it's partial rho by partial time t plus nabla dot rho v equal 0. This is my continuity equation. And the momentum equation is partial rho v by partial t plus v dot nabla rho v equal to minus the gradient of P, the pressure, plus nabla dot mu delta, right? Oh, sorry, this is nabla, and this is also nabla. It becomes delta if we take the mu out, so that's nabla V as well, plus the gravity force rho g. So these are the generic equation right now. So the first example I would like to go through here is actually Couette flow. This is a very famous problem. So first, let's define what's Couette flow. Couette flow is simply driving a fluid flow between two parallel plates. So we have two parallel plates. The lower plate is fixed. And between the two plates, which are separated by a distance h, it's filled with liquid. And what we're going to do, we're going to pull the upper plate with a uniform velocity u. So what's going to happen is the plate will start actually dragging the layer in contact with the upper plate, and that layer will drag the next one due to the presence of the fluid viscosity, and so on until we reach zero velocity here, which we call the no slip condition. So we are expecting fluid will go with different level of velocities, right? Until I reach kind of zero velocity down there. How the profile looks like, I don't know. That's what we need to look into. So again, it's Couette flow. Couette flow as a statement, it's steady, incompressible, fluid flow between two parallel plates. Lower is fixed, upper is moving. And again, it's moving with a velocity u. That's the definition or the statement of the Couette flow. We're gonna establish a coordinate y from here. So at that level, y is equal 0. Then when you go all the way to the upper plate, it's y equal h. So what I'm trying to do here is to use the continuity and momentum equation and do the analytical solution before we jump into the numerical one to see how the velocity profile will looks like inside between these two parallel plates. So let's start with the continuity equation and simplify it. It sounds like the problem is looking for steady, which means that any derivative relative to the time should equal to 0. That's information given in the statement of the problem. And the second is we are dealing with incompressible, so rho is going to be constant. We can also assume that we are dealing with inviscid flow, which means that mu is really very tiny, or the viscous effect can be ignored. and mu is not going to change as well. So that's a inviscid flow. Mu is constant and is not going to change, has no impact. To do that, look into the continuity equation. I will start with the first equation. Let me use pen again. So if I take the continuity equation and expand a little bit, it's partial rho by partial t plus, if I expand that next term, right, it's going to be partial rho u by partial x plus partial rho v by partial y plus partial rho w by partial z, that should equal to 0. So this term will cancel out for multiple reasons. Either it's for steady, so the derivative relative to the time is 0, or it's incompressible, so rho is going to be constant, and a derivative for a constant is equal 0. So that's the first term to be canceled out. And it sounds like we are having actually a flow in one dimension, so we can assume that we only have like one dimension flow, which means that the y and z is not exist. So this and this will be 0 because we're having a one dimension flow. So what we are getting out of the continuity equation is partial rho u by partial x is equal to 0. We know that rho is constant because it's incompressible. It's going to get out of the differentiation. So it's going to be rho partial u by partial x equals 0. Rho cannot be 0. This means that partial u by partial x equal 0. What does that mean, actually? Partial u by partial x equals 0. This is the slope of the velocity in the x direction. So if you look to the flow over a flat surface, if you guys recall from basic fluid mechanics as well, that we form something called the boundary layer. So what's boundary layer thickness? Boundary layer thickness is the thickness above the solid surface where the velocity change from 0 all the way to 99% from the free stream velocity outside that boundary layer. And we know that velocity here is 0. You go up until you reach that 99. So we know that there is a velocity distribution. Initially looks like this. Then it's continue to steep up a little bit, right? Then down a little bit, you will see that the velocity profile, it's kind of repeating itself. So if you look to the slope of this line, here's the slope of the velocity in the x direction. What's happening to the slope? It becomes steeper, but after certain distance, it sounds like the slope remains the same. So in the first region here, we call that developing flow. And as soon as your velocity distribution profile remains the same, we call that actually fully developed flow. So when you see that slope does not change with the x direction, this means that we are in the fully developed flow. So keep that in mind here. When you see the first derivative is equal 0, it's indication of the fully developed flow. So that's what we got out from the continuity equation. Now I would like to write down the momentum equation and see what terms can cancel out or simplified to be able to solve and get the velocity distribution. The target is to get the velocity distribution. Okay, so momentum equation, it's partial rho v by partial t plus v dot nabla rho v equal to minus nabla p plus nabla dot mu nabla v plus rho g. First, we are dealing with one dimension flow. We know that momentum equation can be simply broken into 3 components in the x and y and z. So what we're going to pick is just the equation that presenting the flow in the x direction. So that's easy to do. That's going to be partial rho u by partial t plus U partial rho U by partial X plus V partial rho U by partial Y plus W partial rho U by partial Z equal minus partial P by partial X plus this should be partial mu partial U by partial X. That's totally by partial X, right? Plus partial mu partial U by partial Y. This is totally for Y plus partial mu partial U by partial Z plus G or rho and G in the X direction. This is a momentum equation in the X direction. Now let's simplify the problem a little bit. Number one, we're having incompressible flow. So we said that rho is going to be constant. Mu also will be constant for the inviscid flow, right? Which means that I can take rho out of any of these differentiation terms. Also, I can take mu out of it, right? So rho will go out. So that's rho partial U by partial time t plus U partial U by partial X plus V partial, that's V partial U by partial Y plus W partial U by partial Z equal to minus partial P by partial X plus mu will get out. I'll take mu as a common factor. Then this is the first derivative of U relative to the X. Then you do the second differentiation. So this is partial 2U by partial X squared plus partial 2U by partial Y squared plus partial 2U by partial Z squared plus rho GX. Let's simplify this equation a little bit based on the assumptions of the problem and the what we got from the continuity equation. First, this term is 0 for a steady flow, right? Steady, nothing changed with time, so this will go away. Then we got partial U by partial X equals 0 from the continuity equation, right? So this term is 0 from continuity, so the whole term will goes away. And since we are dealing with one-dimension problem, so this is from the continuity equation. V and W both are zeros because we are dealing with one-dimension flow. So this term will go away for one-dimension flow assumption. Since the flow is driven by the viscous effect or the drag between the different layers, there is no external source. The pressure gradient in the X direction will be actually 0. So this is always equal 0 for no external flow driving force. Nothing is pushing the fluid between the two plates here. It's only driven by the viscosity between the different layers here, which we assume it's constant. Okay, so that's why this term goes away. Then again, if partial U by partial X is 0, so the second derivative of this guy will be also 0. We are dealing with X direction, so the Z1 goes away. But if you look here, you will notice that the velocity is changing in that direction, right? Starting from 0 all the way to the uniform velocity at the top, which means that I know that my U is going to be actually a function of the distance Y, right? So this term exists. I cannot ignore that term, right? Then we're going to ignore, ignore the gravity force. Okay, so the momentum equation ends up to be as follow. All the left-hand side is 0, so everything goes away. So I will have 0 equal to actually just mu partial 2U by partial Y squared mu cannot equal 0, which means that partial 2u by partial y squared equals 0. This is the simplified model or the governing equation that we're going to use to find u as a function of the position y. So again, here is the two parent plates, right? The coordinate y equals 0 here, y equal h in here. The lower plate is fixed, so the velocity is u is equal 0. The upper plate is moving with uniform velocity, u is equal u capital, right? So to do that, let's simply take that equation here and integrate it, right? So if I integrate, first I would get u as a function of y, but there will be the first derivative of u, then I have to integrate again to be able to get the u itself. So if I integrate partial 2u by partial y squared, then I will integrate to 0. This will give me the first derivative, so it's going to be partial u by partial y is going to equal to a first constant c1. Then if you integrate again, I'm going to having u as a function of y is equal to c1y plus c2. So the first observation here, the velocity distribution comes in a linear equation. So I know that I should end up having a linear velocity distribution starting from 0, and the velocity will increase all the way until it reach here. That's u capital. So that's how we figure out that usually the velocity distribution in thin layer between two solid boundaries is linear. So now we need to get actually C1 and C2. To do that, we need boundary conditions. The problem boundaries are located at y equals 0 and y equal h. So I know that at y equal 0, the velocity at that location is 0, and at y equal h, the velocity at h is u capital. So let's start using this. So this will be 0 equals c1 times 0 plus c2. This directly gives me c2 equal 0. I go back to the original equation. This would be u capital equal c1 times h plus c2, which is actually 0. So from this, I got c1 equal u over h. So which means that u as function of position y is equal to u capital over h times y. And this is a very well-known equation for the velocity distribution of Couette flow. Velocity change linearly with the position y, and the slope of that line is simply u over h. That's the slope of this. That's the conclusion here for that Couette flow analytical solution. And why we need that? We need that because when you start using numerical solution, you need to validate your numerical approach and be sure that you are getting the right answer by comparing to the analytical model here. Again, this is more practice of using the continuity and momentum equation to do analytical solution before we start jumping into the numerical solution. Let's conclude that exercise here.